Hi, I'm Greg Sturris. I'm the Chair of Physics and Astronomy at YSU. My training, I have a PhD in atomic physics, and I teach a few different areas of physics in the department.
Awesome. Okay, so why should people be interested in physics?
Everyone should be interested in physics. Physics is for the kind of person who likes to know how things work, but not just, yeah, they kind of do this. They want to really know what's going on inside. Like, have you ever thought about, you take a cup of water and stick it in a microwave, slam the door shut and put it on 2 minutes, it comes out and it's boiling. This is amazing. Maybe it isn't if you've seen it all your life, but it's amazing. You can't take the same cup of water and stick it in something called a micro fridge and have it freeze in 2 minutes. There's a fundamental reason why, and physics will tell you that. So when people get into physics, like, oh, well, that makes sense. I guess that couldn't be possible that way. So there's a bunch of things like that. I mean, is it good enough just to drive in a car, or do you know how the car works? I mean, I guess that's some engineering too, but you know, to fundamentally know how things are going inside gives you insight into a lot of things, I think. So people that like to know how things work should be the ones most interested in physics.
Since you brought this up, why does water boil in 2 minutes in the microwave?
You like that one, huh? Yeah, see, now I'm going to make up my own questions. Well, let's see. In order to boil water quickly, a microwave uses a process where the molecules that are in the water, in fact, water is the thing that works best. If you put, you know, if you have a piece of bread in there or something, it doesn't heat up as much. It does some, but it only heats up because there's water in it. So the actual microwaves have a frequency that cause the water molecules to resonate. They absorb the energy quickly. Let's see, if you're a child on a swing and someone's pushing you, if you push at the right rate, you get going a lot real fast or soon. If you push at the wrong frequency, it doesn't work so well. What I'm saying is the water molecules have a natural tendency to vibrate with a certain frequency, and the microwaves in the oven have that frequency. Get the water jostling up, and then that turns into heat pretty quickly. But trying to freeze something means you have to effectively take jostling energy out. That's not so easy. The best way we have so far is put it next to something that's very cold, right? That's not jostling, and all the jostling ends up, you know, transferring over until it cools down. But that's not a very efficient process. It's difficult to do very quickly. Not to mention, the amount of energy you have to put in water to go from room temperature to boiling is much, much less than room temperature to a frozen block of ice. Changing phase costs you a lot of energy. Those are a couple of issues, I guess, that go into that one. But
Are all subatomic particles the same as themselves? In other words, can you really, like, add an electron to hydrogen and get helium, or is there some fundamental difference between them?
So this is like asking the question, you know, I look at, I don't know, deer in the woods. Can one deer tell that another deer is a different one? Like, that's Bob and this one's Fred the deer, right? Do they look different? Do two electrons, you know, if you were an electron, maybe they look different, right? You want to date another electron, say, something like that. As far as we know, there's this really fundamental thing that particles are indistinguishable. They use that term for it. So if I had two separate electrons, one here and one there, and you turned around and swung around, you wouldn't know if I switched them, because they look exactly the same, right? The same, all the same characteristics: charge, their mass, something called spin that they have. This is pretty interesting, though, because if you think about it, here's what it means. I have two electrons. They can't possibly be in exactly the same spot in space, the same energy level, the same pointing in the same direction, whatever that means, and all of that, because then they'd have to be the other electron. You know what I mean? So it does have an observable effect. There's this thing called the Pauli exclusion principle. You may have heard in a chemistry course or something, where they have they always talk about S electrons, P electrons, whatever that means is something different, but you can put two electrons in each one of these spots as if they could be flipped up and down, it gave us an indication to begin with that there was electron spin, for example. Because we believed they couldn't be in exactly the same place. Well, how can they have the same energy and be on the same hydrogen atom and all of that stuff? That doesn't make sense, because then they would have to be the same thing. Well, it turns out they were slightly different. There was another property we learned they had when we saw that, along with other information. But you know, that was one of the indicators that there was something called
An
spin.
electron in, like, an oxygen atom, the same as an electron in an iron atom. Yes?
We believe so. Yeah. If you switch even if the atoms were side by side and you took one electron in each and did one of those, there should be no way to tell. Like one electron has a blue hat, one has a green hat. No, you know, as far as we know, there is no property that will distinguish one electron from another.
So, I mean, would you actually be able to turn one of these base elements into another by adding or subtracting electrons?
What do you mean, go from oxygen to iron or something like you were talking about? Well, there's differences between oxygen and iron. That's more than just which electron's on it, right? I mean, basically we characterize whether, maybe this is a better question, or something to ask.
Okay.
If I have two iron atoms, are there any differences in them? There could be differences by, well, this one's excited, you know, one of the electrons is an excited energy level or something like that. And as far as I know, there's probably more than one nuclear state it could be in. I mean, even if they have the same numbers of protons and neutrons in the nucleus and the same numbers of electrons, those things all of those items can have different sort of excitations and still be the same thing, right? I guess it's like if I asked if you were still you and you had a big dinner, yeah, you know, you're more excited, maybe more energy, I don't know, or coffee, how about that? You had a cup of coffee, so you're still you, but you're excited, right? You're still you. So there could be differences between groups of particles like that easily. I mean, because we still call it iron if it's iron in an excited state. We'd even call it iron if it had an electron missing, iron ion, right? I mean, they do that in chemistry. So I guess two iron atoms could possibly look different. You know, they could have different energy levels. But when you get down to single particles, I mean, when it's simple enough, you know, and electrons, every electron's the same as far as we know. Every proton, every neutron. It's interesting, though, that protons and neutrons, they're quite a bit more mass than an electron, and yet they have exactly the same charge. I don't know the answer to that question, by the way. So I knew you were going to ask. I'm not sure anyone does completely know the answer to that. But protons and neutrons are actually, because they use the Supercollider to split them up, they found out they're composed of smaller particles. But the electron, we haven't found that yet. Here's an interesting thing about electrons, though. There's two other particles that are very similar to electrons. They have the same charge. Well, I'll just stick with that, same charge, same spin. But there's one's called a muon. They come from, I mean, we see them come from outer space. Collisions from cosmic rays in the upper atmosphere will send muons down so we can detect them. But they behave exactly like an electron, except they seem to have 208 times the mass. So it's like a fat electron. Only they're different in the sense that they don't live very long. I mean, they decay. Electrons, as far as we know, don't really decay. I mean, pretty standard things, I guess. I don't know. That's something else I don't know all the answers about. I don't think anyone does. How long does it take for a proton decay? I think if I remember, the estimate is like 10 to the 21st years. I mean, we're not talking billions and billions. We're talking ridiculously long. For a proton, why is that so darn stable when that thing, that muon, only lasts a couple microseconds or something? There's some insight into those things, but I'm not sure why the proton's so doggone stable. Right? I mean, if things came from some original explosion, why are we ending up with what we got? I don't think anyone knows all of those answers, but, you know.
Here's a question from the web. Margie asks, how do our satellites work? specifically, if Google Earth can get a photo of my neighbor on her front porch drinking coffee, why can't they be focused to help find like the missing Malaysian airliner?
All right, that's a good one. How they work, this is pretty crude, but maybe you could understand it this way. It turns out, I mean, basically you want to be able to take a pretty high-resolution photograph of something that's far away. Right? So basically, how do you make a really good camera? It turns out the size of the aperture that you collect the light with, like the diameter of the lens, basically, the bigger that is, the more detail you're going to see far away. So, for example, if you look at, this is fairly practical application. The pupil of an eagle is like twice what a human's is. But then an eagle has to fly from above and see a mouse, at a great height, typically. So, I mean, that's evolutionarily why, or it's practical anyway. Eagles with big eyes, big eyeballs would survive, right? So the satellites have to have that same kind of design implemented into them. So they're looking down, they have to have fairly big apertures. And I've seen Google Earth, you're right, I can look at my house. It seems like they always take the pictures in the wintertime so there's no leaves and you can see more. But you'll see, oh, it looks like I had, that pile of leaves that I didn't get finished with that, whenever they took that picture. and it's not there now, so I wonder how long that picture was. Because, I mean, they periodically review or update the pictures, and I don't know what their schedule is, but so that I think is the problem with the airliner. I mean, suppose Google Earth was taking a picture of some island. They typically don't take very many pictures of ocean, I don't think, or they don't review them much. Why would you? It's just ocean, right? But if you took a picture of an island, say there was an island nearby the plane as it went down, they happened to be taking the picture, you'd get great photographs. I think the problem with the focusing it on the airliner is if the airliner's already underwater, you can't get much of a Google picture of it.
Kind of been pressing it then, pretty much.
Yeah, I guess you'd have had to time it, right? I mean, that's the idea. I guess if it's somewhere like it's on the bottom of the ocean, but in a shallow enough spot, that it would be worthwhile for Google to look at it. But I mean, if it's too deep, the camera's not going to see in the water. It might be very good for seeing the surface images. But
congratulations, you get to name a newly discovered element. How would you go about doing so, and what name would you pick?
If I get one, boy, I don't know. Naming it, that's the question, huh? This is kind of a side, but this is interesting. One of our astronomers, he's in a project where you look for planets that are circling stars outside our solar system. And I think he has 3 or 5 confirmed planets now. And there's a naming convention, so there is for elements too, obviously, but he was going to name the first planet that was confirmed, he was going to name Winston after his dog. Yeah, now see, that's an option. But apparently they have some naming scheme, it has the date in it and which number and the year kind of a thing. I think they're doing that with the heavier elements after Einstein. I think even one of them they called Einsteinium, like 104 or something. But then there was an argument with some other group that they wanted to call it something else. Anyway, so apparently you don't really get to name them. But what would I name it if I did? Well, I guess if it was discovered at YSU, I'd call it like Youngstonium or Youngstonium, or I don't know. Put us on the map, doggone it, right? I don't know, the thing about trying to find those elements, like they're trying to go heavier and heavier, here's a good question for you. Why don't they find them? I mean, why did the periodic table stop? It's not stable anymore after that. I always think about that. I guess it's a little bit like, now, I'm making an analogy, I think this is how it works. Or if you want to know, that really wasn't the question, but it seems like this is an issue people might think about. I mean, I was going to ask you when you said I found an element, did I find one in between in the chart, or does it have to be a big heavy one, right? In between would really be amazing, because we have every number accounted for. What the heck's going on there, right? Something with half a mass or something, I don't know. how that would go, because they're all accounted for. But the heavier ones, it seems like it's got to be a lot like, I have chickens, you know, at home they lay eggs. So in wintertime, it's cold and you don't get very many eggs. Has a lot to do with how much light they see and everything, but you know, they use most of their energy staying warm, I suppose, and not developing eggs. So if I go out to feed the chickens, I can grab an egg or two from a dozen chickens and bring them in easily, right? Those are the light particles. I guess I'm working against the gravitational force, which is trying to drop the eggs out of my hand, but in the nuclear case, it's a different force, but it's still a force. At some point, you've got enough eggs, so in the summertime, like every chicken might lay an egg, and I'll have a dozen eggs to carry in, right? And I'm having a hard time, and every once in a while you drop one or whatever. I mean, if you have a bucket or something bigger, but let's suppose all you got your hands, and in the nuclear case, all you have is the nuclear force. It has a certain range. So after you start stuffing so many things in there, it's having a hard time stably keeping it together, right? So I guess it's a little bit like the egg carton issue ordeal, whatever. I mean, if we could get a bigger bucket for the eggs, I don't know how you make a bigger nuclear bucket. You know, the nuclear force is really, it's strange. It's a short-range force. Like, you know, if you had a nucleus where you're sitting and where I'm sitting, I had a nuclear particle. You know, you had a neutron and I had one. I don't want to hold those, but, you know, they're supposed to attract one another in the nucleus. Why wouldn't we feel it outside that? Because it's not a very strong force very far away. So I guess I don't know. I make an analogy with the egg basket thing, and I figure that's where they're done. Now, I don't really know how you make an analogy for, I guess maybe it's like this. You know, they predict that there may be, in the periodic table, like they've gotten to the highest ones, they don't live very long. They like break apart fast. So you don't, they're not stable enough, are you even going to call it an element? I mean, how long does it have to sit there for you to say, yep, it's an element? I don't know, right? But I think they're predicting that there's a little, they might expect an island of stability a little further out based on patterns in the table. Like there might be something at say they're at 105, maybe 10 now. Maybe there's something at 120, 128 that's really stable. And so, but getting out there, of course, you got to filter your way up to get out there. I don't know what analogy you'd make. Maybe they've figured out a way to have, you know, a basket in a pocket or something, right? And you can carry some more eggs or something like that. I don't know. It's interesting stuff, though. I mean, the people that are doing that kind of research have a lot more insight into where they expect these things to occur. Mine's pretty simple thought about it, I guess.
Well, your analogy actually reminds me of another question. The Bohr model of the atom.
Oh yeah, no, I like that. See, that's atomic physics.
Seems more practical mathematically, but my understanding is the electron cloud model is falling more into favor. Which one do you prefer? And as far as your analogy goes, wouldn't the electron cloud allow for more stability?
Yeah. Well, the Bohr model. Wow, Bohr. There's a whole bunch of stories there. You know, Bohr and Einstein used to argue all the time about things. I've read books about it. They're pretty interesting discussions. But Bohr was really sharp. I mean, the model he had, he developed it in 1925, 1926, something like that. It made a few sort of upfront assumptions. I guess the whole thing was, the way he did it was he said sorry about that noise. The angular momentum of the electron in the hydrogen atom could only have fixed values. That seems strange. I mean, angular, probably don't think about that stuff very much anyway, but angular momentum, if you've seen a gyroscope, you know, they try to use those for, well, they do use those for navigation. Once you get this thing spinning, it tends to point in the same direction as long as it's mounted on something that allows it to rotate freely. As you turn, it will keep pointing the same direction. So for a large-sized object like a gyroscope, you could have it point in any direction you want at all, right? You spin it and set it to that direction, that's what you got. But what he was saying is the electron can only sort of rotate around and make it spin in certain directions. Why? He didn't say why. He just said, let's suppose that's the case. When he did that, and you look at the rest of the properties of the atom, like the energy of the atom, the spacings between energy levels, they actually match hydrogen very, very well. So you can't just say, well, that's a stupid idea you had. I don't know why you had that. Well, because everything works after that. That's actually pretty good. Maybe there's a better reason to pick that idea, and then everything's good. So later what was found is, you call it electron cloud, it's wave mechanics, treating the electron as if it were a wave instead of a particle. And waves behave quite a bit differently than particles. For one thing, they like to have certain value, they like to be quantized, right? If I have a clothesline tied at the two ends and I jiggle it, it has certain ways it likes to jiggle and resonate, and those are the fixed, things for the fixed energies, if you like, for the clothesline. So the same thing happens if you put a wave in a circle. The Bohr models, or the atom's a circular box instead of a, so then you find that the energy levels, and you find out, it turns out, going from that direction, that the angular momentum is quantized when you make it a wave. So everything Bohr sort of hypothesized and then found, you can show by thinking differently about how you do the mathematics of the atom. And, well, so I guess, I don't know that anybody's like arguing about is Bohr right or is the wave mechanics right. They believe the wave mechanics is the way to do it. There's even, more than that if you go on. If you think the electron behaves like a wave and that helps you understand hydrogen, maybe things like light, which we think is a wave all the time, sometimes acts like a particle. And will that help us understand how it turns out? Throw that in, you get even higher accuracy in the hydrogen atom. The big problem you have is, once you get to anything bigger, the next one's helium, right? 2 electrons. Things get a lot more difficult quick, Whenever you have, well, it's the same as the question you had about, are these two things indistinguishable, right? 2 iron atoms are a pretty complicated system when you're going to make every particle inside them a wave, right? Now, even if they're particles, it's complicated. How do I calculate where, let's say you have 3 particles bouncing around in a box. How do I calculate where they go? It gets pretty complicated, right? Just because there's more of them. Making them all waves doesn't help at all, make that easier. So we get stuck pretty quick in atomic physics with the multitude of particles. You have to find ways to estimate, approximate this as a sphere and then have this outside it, and do different things like that.
Could you explain, because this is big in the news, or used to be, how does the Supercollider work?
All right, so if you want to make something go fast because you want to smash it into something and see what happens, let's just stop there for that part of it. Probably the easiest thing to do is find something light, because it'll be easier to push, right? And then find a way to push it. I mean, how do you push an electron when you can't even see it, right? They don't actually use electrons; they use protons. Okay, so you start with protons, which is, I guess, about the smallest particle you could imagine that's got something structure-wise in it. They already know that now, but they only know it because they smashed them together to start with. But anyway, so they start with the protons, and typically, like maybe the simplest way you could imagine doing it is a charged particle like a proton, a positive charge, when it sees an electric field, like hook up a battery between 2 plates, there'll be an electric field between them, one side's plus, one's minus. The protons want to get away from the plus towards minus, like particles repel, opposites attract. And so for the proton, the electric field looks like a hill, like it would for a ball. So I put the proton near the plus, wants to roll down to the minus. So first thing they do in the Supercollider is they have what they call a LINAC, a linear accelerator, that takes the protons and speeds them up. Actually, the largest fraction of their speed increase is done that way. But the problem with doing that is you have to have, so you could keep going faster and faster with a bigger and bigger hill, right? Bigger and bigger electric field. But pretty soon you have such a big electric field that it's going to spark and arc to, it's just hard to make something that big to just straightforward push them faster. So what they do is they speed it up in a linear accelerator. You can imagine then, if you put it in a circle, you think, well, I know they do a circle, maybe that's the way they do it. But if the hill goes in a circle, it doesn't, you can't keep it going more than one time around or whatever. You're going to go in a helix down. So what they end up doing is injecting it, actually do a couple things. They inject it into a set of rings that splits the proton beam up. So a little bit of the beam goes into, I think it's 4 different rings. That's the beginning of splitting it into, they like to have it in packets. So when you think of protons going around this big circle that the Supercollider represents, say more about that, but you want it to be in little bunches because it's easier to, I guess simply thinking about it, it's easier to give each bunch a kick than to try to continuously have all of them speed up. That's not very, I wasn't very clear on why that is, but that's really what they end up doing. So I guess you think about it like this. So they split it into four. There's four rings that are stacked on top of each other, and I think those aren't huge. You know, the big ring for the Supercollider is like, I think it's 27 kilometers around in circumference. You know, it goes in France and Switzerland, right across two country borders. It's right on the edge. I think they did that so the collaborations would always, you know, if you put it in France, after a while the other country doesn't fund it for whatever reason. You know, I guess, I don't know. I mean, there's a lot of countries working on it that aren't just Switzerland and France. But so it's a huge ring. Before they get to that, they have smaller, I don't know if there's 2 step-up rings or 3 before they get to the big one. But in each one, you can imagine doing this. Now, I can't make the hill go around and connect to the top of the hill and keep speeding it up. But I can make each bunch think there's a little hill as it goes by, so to speak. So think of it this way. So I have a kid on a merry-go-round, and the merry-go-round doesn't have any bars or equipment. I want it to go faster. Every time the kid comes by, I can give the kid a little bit of a shove. If I do that at the right rate, I can keep speeding the kid up. Actually, with the bunches, think about, I don't know, 4 kids and 4 adults standing around. Each of them pushes at exactly the same time. So they call that, it's an alternating electric field. It's actually a radio frequency RF field that they use. And so it's at stations around these round rings, giving them little kicks each time and, you know, speeding them up. They actually do it over a couple rings. I think that's just to get it up to the top speed. I think, if I remember right, they don't split the two. Okay, I don't know if you know, but so suppose you have these bunches of protons going around the ring. You manage to get them going fast. You really want to have, well, I don't know if you want to, but this makes sense. If you can get protons in another beam pipe, say one's high, one's low, one's going this way and the other one's going that way, the bunches. So when you do the collision, it's basically twice as much energy when they come together. I mean, you're trying to get as high energy as you can. And there's limits to even how fast you can get them going by giving them little kicks. You know what I mean? I mean, sort of doing it the smart way is still got a limit. So if you double it, at least, if you have them going opposite ways. So basically, on the ring, you got a charged particle. I don't know if you've ever seen this. It's the reason we have the northern lights, I guess the southern lights too, but since we're closer to the northern ones, that's what we talk about. If a charged particle, like from cosmic ray or something like that, comes near the Earth has a magnetic field. And the magnetic field lines, it turns out, charged particles like to go in circles around magnetic field lines. It's, let's see, we have a pretty cool, in fact, you need to show you this actually, but we have an experiment we do in the introductory lab where electrons are shot out of a little filament gun, and you put a magnetic field on, you watch them go in a circle. And you change the field to see, yeah, they're in a tube that has mercury vapor, and so when it hits the mercury, it glows blue. And so there's a little blue circle, and you can change the radius of the circle by changing the magnetic field. It's, I guess, the same thing as this. The old TVs, I don't recommend doing this if you have one, but if you have a big magnet in an old TV and you put it next to it, the whole thing goes like this, because it's an electron beam hitting the phosphor screen, and the magnetic field causes it to bend. If you know the direction of the field, you'll actually find out pushing the field this way makes the particles bend this way or that way. It depends on what the charge is on the particles. But anyway, so a charged particle and all of that. Charged particle in a magnetic field just changes direction, but it doesn't really speed them up. So in that ring, they'll have magnets that keep the protons going in the circle, but that doesn't speed them up. They need those electric field pulses to give them kicks as they go around. And then the magnets keep them in the circle. Basically, they're for steering. I mean, they do some steering with... It's way more complicated than that, but at least the two basic things are the magnets keep them in the circle, and the pulsing electric field helps to speed them up. So then they get to these fast protons coming in, and they smash them together to see what comes out. That's a complicated thing. You should see the detectors they have for seeing what comes out. I mean, it's, you know, the size of this building kind of big detector-wise. It's huge things they put together. All of them are based on some characteristics of the particles. If they're charged particles, like I say, that's a That's convenient because you know in a magnetic field a charged particle will curve. If it's positively charged, it goes one way. If it's negative, the other way. So if you know your magnetic field, you can right away say, oh, I made a positively charged particle, I made a negatively charged particle. The size of the charge depends on the speed of the particle and the size of the radius that the thing will go in depends on the charge on the particle and the speed of it. If you can determine the speed somehow, then you're measuring the charge by measuring the radius of the surface. So they use that technique for figuring out how much charge is on the particle they make. I guess, really, if you think about it, they don't just bash things together and see what comes off. I mean, they do see a lot of things come off, but they're, you know, people predict where they think the next massive particle would be. You know, like how fast would you have to go to split this thing off? There's various theories, and of course that's what they're developing as they find them, right? So no one knows for sure, gee, if I go this fast, I'll get another particle. If I go twice as fast, I should get that one and another one. They don't know offhand. They're still developing the ideas. But as far as I know, they're getting close to having the whole, it's a different table. It's not a periodic table, but it's a table of high energy particle physics. I don't know if you've seen that. The version I have up in my office is probably 10 years old. It's a pretty standard one you can find in books, but they found, you know, I don't know if you've heard, but the last of the quarks, the top quark was, what, a year or two ago? They believe they found that. So, I mean, I don't know if they're wrapping all that up, though. I think there's a lot of understanding that has to go in. Probably still needs experimental work done to figure it out. I know they're not very close on you know, gravitons, gravitational waves. Gravity seems to be a real bugger on sort of, you know, looking at all the different forces we have and how well we understand them. Gravity is the one that's being the most elusive as far as observing its particular wave-like properties, particle-like properties, that kind of thing. So that doesn't tell you that much about what they did exactly at the end. Maybe it helps you understand why they're making it in a circle. I don't know how else you'd speed it up. If you do a linear thing, you're in trouble, because you just can't keep going downhill, right? You can think of making a ball roll fast by rolling it downhill. Find a mountain, great. Want to go faster, then dig a hole, great. How long can you do that, right? You're stuck after a while. The circle idea was pretty slick. Whoever thought of doing that? Wasn't me. Darn it. Well, let's see. You have rules that you can measure and follow. You know, particles obey these rules. You push on something, it starts to accelerate. You push on something that has less mass, it accelerates more. So you think, well, there's a relationship between acceleration and mass. Newton's got all that down, and we use those. This non-Newtonian physics, I think it's branching off. There's something called non-Newtonian fluids. When Newton described a fluid, it's a specific way that the stress and strain on the fluid behave. I guess basically it's a model like this. If you think of a fluid, maybe in a pipe, as sheets of molecules of liquid, and you try to describe how they behave when you push on them and things, you get a model like Newton. Well, if you're really smart like Newton, you get a model like Newton had. And it describes most fluids, like water in particular, which everybody's pretty used to. But there are some fluids that don't behave like water at all. I don't know if you've ever gone, you can go on YouTube, I think has these too. And I don't know what fluid they were using. It looked like a milky structure, but it was probably some colloidal suspension. Turns out...
Like cornstarch and water.
Is that what it is?
Yeah.
It could be.
You mix them together and...
Because if you have a pool, I mean, they had a... well, it was basically a pool. Something looked like about 3 feet wide and about 12 feet long or something. And you could tell it was the liquid. You know, you push on it, it's like sloshing around and it's white. So it could have been a cornstarch mixture or something. And the guy that was doing it wanted to show how it was non-Newtonian. See, a Newtonian fluid, if you push harder, it will spray out faster. Say. This stuff behaved differently. The faster you push, the more it acted like a solid. So these guys walk across on it. Well, they do it pretty quickly, but as you slap your feet on it, you can walk across on the liquid. But if you step into it, you sink. So it's not very Newtonian. The model for Newtonian fluid is the harder you push it, the faster it'll respond with a spray or something. I mean, that's not very technical, but that's the idea. And that's not how this stuff behaves. But there's a lot of fluids that don't behave that way. I mean, I guess like even shaving cream is non-Newtonian. You think about, or even pudding, right? If you slowly scoop it up, it's like a solid. But if you try pushing through it, it acts like a liquid would. You know, it's just not Newtonian. But that's a very precise description, right? People are going, non-Newtonian fluid. Well, then I know that has a different property. What's that stuff called? They used to get it in an egg.
Silly putty?
Silly putty, yeah, that's not Newtonian. You know, it's almost a solid most of the time, really. I guess that stuff flows. That's just weird about, one of your basic definitions of a fluid, or a liquid, I guess, in this case, is that it flows. What if it takes 3 centuries to flow? You know what I mean? Like, I suppose there's some, there's some materials we would consider solids, right? Because I died before it flowed enough for me to measure it. So that's a solid as far as I'm concerned. But it's that kind of thing, right?
Like glass?
Yeah, I know people argue about that one. We had a glass laser tube in where I used to do my research as a grad student. And I went back about 20 years later, that same tube was still there. They were using other lasers, but the same tube was there. And this may have to do with it's been heated too when the laser was on, because it's glowing. And then, of course, a fluid, oftentimes if they're heated, flow more easily. Not always. That's an amazing question. There's a question. Well, I'll get back to that. But I looked at the tube, and you could see down the tube that it sagged, and it never used to be straight. Because it had to be straight in order for the laser light to go through it. You can't bend the light up and down along the tube, it's going to go straight. And the tube was almost unusable, because you could see it was about half the diameter of the path for the gas. It had sagged. What was, I don't know, about 2 meters long, and it's supported at the ends, not in the middle. So, as time goes on and it's heated, it's starting to sag. So it seems like glass does act a little bit like a fluid. The fluid, I was going to say, is amazing, because this amazes me. The oil you put in your car or whatever. I have an old tracker at my barn, and it's supposed to use 30 weight oil. That was back in 1929, maybe 39. It's an old Ford. They didn't have multi-viscosity oils. The stuff you buy now is 1040, 530, whatever. What that means is it behaves with a viscosity or a weight to the oil of 5 when it's, say, at room temperature or cold. When it's heated up, it acts as though it has a heavier weight, which is the opposite of what you think fluids do, right? I mean, normally. So that's just, it amazes me they can engineer something that, does that. But I mean, it makes sense. You need to have it be a certain weight while the thing's operating, and the hotter the thing gets, you can't have it be less weight. I mean, less viscosity, it's not going to lubricate the parts, right? So I was thinking of changing my Ford oil from just 30 weight to like 10W30. So it would start when it's cold, and then it would heat up and have the viscosity it needs. I haven't gotten around to it though. Too busy with the chickens. There's often somebody who stands out and proclaims, look, I got this better than physics does. And maybe they do have an idea. You have to look at them. But the idea is, typically it won't take all of the physics that we already know works pretty well and completely flip it on its head, right? It's going to be, oh, in certain conditions, this is a better way to look at the system. Maybe that's the case. It'd be nice if people would publicize what they're doing in that way, because more people would look at it more seriously and maybe get more out of it. And you want people to look at it, critically and maybe join in and understand it. It's not a good idea to say, hey, everybody else is wrong and I'm right. It really just doesn't work. I mean, even if they find out later they are all wrong. I mean, who knows? Maybe you'd find that. But you can't get people to seriously look at it without having some idea of going from where they are to where you are. Okay, throw away all your ideas and jump on my bandwagon. I mean, that doesn't work very well.
You know how doctors will watch medical shows with a critical eye, and lawyers will watch law shows? Do you watch, like, The Big Bang Theory with a critical eye?
Oh, well, I watch Big Bang Theory all the time. Yeah. In fact, the problem with the critical eye thing is, if you're watching movies, the person watching with you doesn't want to hear your physics comments. You know, like, hey, by the way, they could never do that because X, you know, or whatever. But I think you find out that physicists aren't like doctors. Like, okay, so a doctor might watch a medical show and go, that's not what we do to test that, and that wouldn't indicate whatever. Physicists can do that about a show that's like a movie that's supposed to be real life. A plane does something, maybe does something amazing. You know, that wouldn't happen maybe. But a lot of times physics people love science fiction. So they're willing to accept the sort of guidelines that there's some, I don't know, a particle rearranger that'll take you into pieces and shoot you to a planet and then reassemble you, you know, so that the story can go on because they like the story anyway. So they tend not to be, I think, most of them tend not to be, you're not going to be able to make one of those. Well, come on, that's the whole story, or we don't have any fun here, right? But yeah, I watched The Big Bang Theory though, because it's really cool. They have, I think they have whoever does their advising for their backdrop. A lot of times the equations on the board, I'm thinking, hey, we used those in class the other day. You know what I mean? They're real equations. So somebody's, and when they show the labs, most of our labs, this one actually doesn't happen to have it, but most of our labs have an optical table with some lasers on it and stuff. And that's what it looks like when you walk in a physics lab. So they obviously went down there and found one and said, oh, let's make it look like this a little more. It's a little cleaner than our labs, though, I noticed. If there's anything to criticize, it's like, boy, the lab would not be that clean. You know, but maybe I shouldn't say that. We should keep our labs cleaner, maybe. Yeah. No, nobody ever calls and says, you know, I got a hydrogen atom here, and there's this thing going around. Is that the electron, or what is that? You know, nobody ever calls me on that. It's strange. Yeah. You'd think they would, because it happens all the time.